Hello everyone, and welcome to another Leetcode video. Today we're looking at the problem Count the Number of Winning Sequences, which was question 3 in a weekly contest 419. So the question reads that Alice and Bob are playing a fantasy battle game consisting of N rounds, and each round they're going to summon one of 3 magical creatures. We have a fire dragon, a water serpent, or an earth golem. So in each round, players will simultaneously summon their creature and will be awarded points according to the following rules. So if one player summons a fire dragon and the other summons the earth golem, the player with the fire dragon is awarded a point. If one is water and one's fire, water is awarded a point. If one is earth and one is water, then the earth gets a point. And if both players play the same creature, then no point is awarded. So you'll see later on, but essentially these are the rules of rock, paper, scissors. We just need to keep track of those relationships and how they work. So we're going to be given a string S consisting of the characters F, W, and E, representing fire, water, or earth. And this is the sequence that Alice is going to play. So we don't know what Bob's sequence of moves is going to be, but it's guaranteed that Bob will never summon the same creature in 2 consecutive rounds. If Bob beats Alice, then the total number of points awarded to Bob after N rounds is strictly greater. So, in other words, if Bob has more points than Alice when we get to the end, then he wins. And we want to find the distinct number of ways that Bob can beat Alice using these rules. So, this description is pretty complicated. There's a lot going on, but essentially, we're going to be given a string with Alice's choices, whatever she plays, and we also want to figure out the number of ways that Bob can beat her playing by these same rules. So looking at this example, we have FWEFW, which represents Alice's choices and her turns. So we see that there's 18 ways that Bob can beat Alice. And I'm not going to list them all out, but you can see, for example, one is FWFWF. If Bob plays this, it guarantees that he's going to have more points than Alice at the end. So let's look at an example and see exactly how we can figure this out. So let's take a closer look at this example. So we're going to look at FWEWF, which represents Alice's moves. And over here, you'll see that I just kind of outlined the relationship of these different creatures and what beats what. You'll see it's a kind of a circular pattern, very similar to how rock, paper, scissors work, where if you pick one, say for example fire, and the other person picks earth, then you would beat that person. If they pick earth, you pick water, they beat you. So we could just kind of reference this as we go through to see what would happen if we make certain choices. And choices is really the key term here. We have to make a choice at every step to play a specific monster. So, for example, if we're at this first F, we know that Alice is going to play a fire monster. Well, we could either play a fire monster, and if we get this, then there's no points, right? Because we're playing the same one. We could play a water monster, right? We could play water here, and here we'd get a point because we beat Alice. Or what we could do is we could play the earth monster, but if we do this, then Alice beats us, and we would kind of lose a point because Alice would beat us in this turn. So you might just say, why don't we just reference this and always just play whatever beats whatever Alice is playing? Well, good idea, but there's one constraint that we cannot play the same monster more than twice in a row, right? So here, if we were to play water, right, then we know that in the next turn, we couldn't play water again. And in this case, it doesn't really matter because, Alice plays a W, and if we played a W here, we wouldn't get any points anyway. But there might be a case where maybe playing the monster that wins in this case is not really the right approach. Maybe we want to play a different monster and save the same monster for a later turn. So we have to make a choice, and we don't know what the optimal choice is going to be, so we have to try them all, which means that we need to use dynamic programming for this question. So how exactly can we use dynamic programming here? Well, like I said, we literally just have to try all the choices. So we can go through all the indices. Let's start here, and we'll just try every choice. So we could say we have an F. If we play F here, we get 0 points. If we play W, we get a point. If we play Earth, then we know that Alice gets a point, right? So we could put -1 here to represent Alice getting a point. So we have to basically go through every index, and we have to keep track of a couple things. We want to keep track of our index, right, as we're going through. We want to keep track of Bob's score. We want to keep track of Alice's score. And we also want to keep track of whatever we played previously. And why do we need all these things? Well, index, we need to go through the string, so we need to know where we are, right? So this can be up to 1,000. And why do we need these two scores? Well, we need them because we need to know at the end if Bob's score is strictly greater than Alice's score, right? So we need to keep track of the scores as well. So this can be up to 1,000. This will happen if Bob wins every round. And this could be up to 1,000 here, Alice's score, if Alice wins every round. And previous, we only have 3 values it could be. But you might see a problem here, right? If we're doing memoization, this is actually 1,000 times 1,000 times 1,000 times 3, right? So we'll see that if we keep track of all these things, it's going to be way too slow, take way too much memory, way too much time. So we need to find a way to kind of simplify this problem down a bit. So what we could do is we can actually take these two elements here, right, Bob's score and Alice's score, and we can simplify them down into one. And how do we do this? Well, rather than keeping track of the actual scores, what we can do is keep track of Bob's score relative to Alice's score. And what does this mean? So let's say we start with a score of 0. And let's say Bob wins a round. Let's put B here for Bob. Well, we could say, let's say Bob now has 1. Our score is 1. And let's say Bob wins again. Let's say we have 2. But now what if Alice wins? So instead of having another variable, let's just say we're going to take whatever we saw previously and subtract 1 from it. So now our score goes back to 1. So what are we really doing here? Basically what we're saying is this is Bob's score, these values, relative to whatever Alice has. So if Bob ever wins a round, we will add 1 to this value. And if Alice wins a round, we will subtract 1 from this value. And if it's a tie, we just don't do anything. So how does this help us? Well, now what we're doing is we're doing 1,000. And we know that we're simplifying down these two numbers into just one of these, right? So now we're doing 1,000 times 1,000 times 3. And this is a huge benefit because we're basically doing 1,000 times less work than we would do if we had to keep track of both, right? So basically what we're doing now is we're saying we're going to go through each index, and for each index, we want to see the problem relative Bob's score to Alice's score, and we also need to keep track of these 3 potential values, right? So this is really a DP problem, but the hard part is figuring out this optimization here and how to make sure that we can simplify the score down into a simple way that won't do too much work. So what's the time complexity here? Well, I kind of laid it out here, but if we call this n, and this is just kind of a constant value, we can see that we're doing n times n, so at most, we're going to be doing n squared work here. Let's hop over to the code and see exactly how we could solve this. So the first thing I do here is just set up my memoization object just to save values that we can use again later. Then I'm going to set up my recursive function. And what I'm going to do here is that just have 3 arguments, our index, our score relative to Alice, so not an absolute score, but relative to Alice's score, and then just our previous, which will represent the previous creature that we played. So our base case here is if we get to the end and Bob's score is greater than 0, we want to return true. So what does this mean? Well, we know that if Bob's score is greater than 0, this actually means that Bob at this point has more rounds won than Alice. So remember, we're keeping track of the relative amount of rounds won compared to Alice with this value. So if this is ever greater than 0, we can just return this at the end with a true value. Then what we do is just grab whatever value we get from the string and instantiate an answer variable. So then we're going to go through all the creatures that Bob can potentially play. If we see that the creature is the same as the previous one that we played, we know that we can't actually use this, so we just continue past. Then we have a couple different things that we need to check. So if the creature that we're playing is the same one that Alice is playing, this means that neither of us gain any score, so we're just going to move on to the next index. Then we check if Alice beats us. So If she does beat us, which are any of these three cases, then what we want to do is we want to subtract 1 from our score value. And this represents that we are losing some ground in our lead on Alice. And otherwise, if we beat Alice, then we want to add 1 to our score. This represents gaining some lead on her. Then at the end, we're just going to return our answer, but make sure we mod it by the value that we're given because the answer can be very large. So let's submit this and make sure that it works. And it does work. So hopefully this is helpful and it made sense. Thank you for watching.